Yeah, so some technical glitch. Okay, yeah. So in particular, there exists a constant such that minimum of this function mod of f prime x over this interval r minus delta 1 to r plus delta 1, this minimum will exist. Why? So this minimum exists because f is considered to be a C2 function, which means this f prime is a continuous function, so its minimum will be attained as this interval is a compact interval, and we are letting this minimum to be m delta 1. And again the maximum will also exist. So since f double prime is a continuous function, because f is considered to be a C2 function, so f double prime is a continuous function. So there is a L delta 1 greater than equal to 0, such that maximum of this, now we are taking maximum of f double prime, so without loss of generality we can assume that this L delta 1 is strictly positive, because if it is 0 then f double prime over this interval will be 0. So without loss of generality we can assume that L delta 1 is strictly positive. So thus we get, you remember mod of en plus 1 we have already computed. It is, it is this quantity in the square box, in the rectangular box. So it will be mod of f double prime zeta n by 2 times mod of f of x n times mod of en square. You see, because zeta n was in this interval r plus minus delta 1 and x was also in this interval, yeah, so we will actually have this L delta 1 by 2 m delta 1 times mod n square. So by choosing, so you just note that delta 1 goes to L delta 1 by 2 times m delta 1 is an increasing, that is non-decreasing function of delta 1. Because if you take smaller delta, then your maximum will also be smaller, right? So you just prove that this is a non-decreasing let this function be c delta 1. So this non-decreasing function of delta 1, hence c delta 1 remains bounded as we increase the value of delta 1. Thus there exists a delta less than 1 such that delta is less than delta 1 and delta and c delta is less than 1. Now our aim is we show that this delta has the desired property. The desired property being the conclusion in 1, 2 and 3. Yeah. So we have inequality here. Let this inequality be 1. So what does it read? So inequality in 1 shows that mod of n plus 1 is less than c delta mod of n square. Now with this we prove 1 and 2. So proof of 1 and 2. Proof of 1 and 2. Now let x naught belongs to r minus delta to r plus delta. So that is x naught minus r is actually okay because center is r. So r minus x naught is less than equal to delta. Then you see x1 is, what was x1? If you start from initial guess, x0 is the initial guess. So x1 will be x0 minus f of x0 by f prime x0, and this is going to be well defined as f prime x0 is non-zero since x0 belongs to the interval r minus delta to r plus delta, on which f prime x is never 0. Correct? So x1 is well defined. Now let us show that x2, which is given by x1 minus f of x1 by f prime x1 is well defined. See, this is also well defined if we show that f prime x1 is not 0, but this will be true because you see r minus x1 which we know is E1, and this will be less than equal to C delta E naught square, and the way delta has been chosen, we know that E naught is actually less than delta, so we can use that fact. Okay, why? Because see, this particular thing was E naught, right? So E naught is less than delta, less than equal to delta, and this is less than equal to E naught, correct? Because C delta, because delta C delta is less than equal to 1, the way we have chosen, and this is precisely, again I am writing R minus X naught, and this is less than delta. So all this jargon is to prove that x1 belongs to R minus delta to R plus delta. So this shows that, just a minute, so this shows that f prime x1 is non-zero. So by induction you keep on doing this. By induction it follows that each xn is well defined. So this was the statement 1, right? And secondly, you see xn minus r is actually delta for all n. So this proves the statement 1 and 2. Now let us move to the proof of 3. So from the inequalities, we get that, you see, what was En plus 1? We have, as proved above, it is less than equal to C delta mod En square. Now En is actually less than delta, so we take one mod En less than equal to delta and one mod En as it is. Okay. But again you use this inequality, on En, so you know you will get this happens for all n, right? This happens for all n, which means if you apply same inequality on En, you will get C delta delta as it is, and for this En you will get it is less than equal to C delta delta mod En1, right? So yeah, so ultimately it is C delta delta square mod En minus 1. Now if you keep on doing this inductively, you will get that this is actually less than C delta delta power n plus 1 times E naught. Now E naught is a fixed number, and so from this inequalities the convergence of the sequence follows as delta times C delta is less than 1, right? Why? Because we know alpha n goes to 0 as n goes to infinity if mod alpha is less than 1. Okay, this is a result from real analysis and it is not difficult to prove. Yeah. So with this, yeah. So what was Gn plus 1 actually? So this implies, so consequently, limit En plus 1 is 0. But what was En plus 1, or actually mod En plus 1? So this was actually xn plus 1 minus r, right? So this implies limit n goes to infinity, xn plus 1 is r, or we can say xn is r. And this was the last thing to be proved in this convergence theorem. Yes. So far we have seen the new what does in the last tutorial session we discussed the geometric interpretation of Newton-Raphson method. We revisited that here for the sake of completeness of this lecture. We derived the formula and then we compared it with secant method. The comparison is not very difficult to see. In the secant method, where we need 2 points of initial guesses, in Newton-Raphson we just need one. So it might be very tempting to believe that okay, Newton-Raphson method works better. But you see, in the secant method there was no f prime term. Okay, just continuity was sufficient to actually apply to the secant method irrespective of the convergence. Here it is not the case. You have to ensure that the first derivative exists. Okay, so Newton-Raphson method is applicable to at least once differentiable functions. Okay, then we saw some examples and then we saw this convergence theorem. The hypotheses are same as the secant method. We start with the C2R function and consider its simple root. By simple root of f, we means that it is a root of f and its multiplicity is 1. Its algebraic multiplicity is 1. So it comes out as a linear factor, that is f prime of that root is never 0. So then we saw conclusion is the conclusion basically says that if you're starting your initial guess sufficiently close enough to the simple root, then the iterative sequence will be well defined and will be sufficiently close to the root r such that it converges to r. Okay, that is the simplest way a Newton-Raphson method convergence can be explained. Okay, we will see one more convergence theorem for convex function. So as discussed, theorem on Newton-Raphson method says if you start nearby a root of the non-linear equation, then the Newton-Raphson method iterative sequence is well defined and it converges to the root. This is precisely the statement we just seen. Now for increasing convex function, we'll see that for increasing convex function, we need not be very careful where we are starting from. See, the point is, in all these bisection method, secant method and Newton-Raphson method, you have to start initially with very close to the root. So it's a paradoxical situation in the sense that how would we know we are starting with a sufficiently close guess to the root. But there are certain class of functions for which we do not need to be worrying about that, and that is precisely increasing convex function. Yes. Yeah, so we don't need to be very careful in choosing the initial guess. In choosing the initial guess. For such functions, the Newton-Raphson method iterative sequence always converges. See, that is the good thing about this class of function. So whatever your initial guess is, whatever the initial guess is. So this is precisely the content of the next theorem. So okay, let us put it like a theorem, okay, and we will prove it. Theorem. Convergence result for convex function. Let us call it like that. For convex function. Yeah. So the statement goes like this. Hypothesis. Let f from R to R be a C to R function. So already we have seen a convergence result for a C to R function such that f is convex. Now what does it mean? By convexity it means for C to R function it means the second derivative is always positive. Second, it is strictly increasing, right? We have to assume that f is strictly increasing. That is, derivative is also strictly positive. And third, there exists an R such that f of R is 0. That is, f has a root. Okay, f has a root. So if you assume strictly increasing convex function which has a root, then the conclusion is number 1, R is the unique root of f. Secondly, for any choice of x naught, the Newton-Raphson method converges. the Newton-Raphson method converges to R actually. So let us prove it. The proof is not difficult because we have already seen the proof of the convergence of the Newton-Raphson method. It's actually pretty derived from that. So proof of 1. Now since f is strictly increasing, what does it mean f is strictly increasing? Let's say f has a root here, okay, and if f is strictly increasing, so hereafter it will keep on increasing, right? And then it should be like this, right? Something like this. F has to be something like this. Otherwise, any increasing function, if it intersects x-axis, it will intersect only once, okay? So this is precisely what I am writing. Is f is strictly increasing, the function f cannot take the same value more than once. So thus f of x is 0 has exactly one root. So this was the proof of 1. Now let us move towards the second. See, we have already proved in the previous theorem from the previous theorem proofs, we have this, right? En plus 1 to be minus f double prime zeta n. Let me join. Just a minute, how will I? Yes. So let us put it on full screen. Yeah, now it is fine. So f double prime zeta n by 2 f dash xn by en square. We have already seen this. And so it implies that so it shows that because everything is positive, this thing is positive, right? So it is actually negative. So hence this was r minus xn plus 1. So r is less than equal to xn plus 1. And since f is strictly increasing, we get that f of r is actually less than equal to f of xn plus 1. And this precisely means that because this is 0, so thus what does it give us? it gives us that f of xn plus 1 is greater than equal to 0 for all n in n. Yes. Now you see, what was our xn plus 1 minus xn? It was minus f of xn by f prime xn. Now, so you use this. Now here everything is positive, so this part is positive, right? So this box is actually positive, so this becomes negative. So we get that xn plus 1 is actually less than xn for all n, which means xn is a decreasing sequence. So hence this sequence xn, this is a non-increasing sequence, or actually this is a non-increasing sequence. And is bounded below by R, right? Yeah, this you see, this is the bound part and this is the non-increasing part. So together this implies from it. Now from monotone convergence theorem, it follows that from monotone convergence theorem, it follows that xn converges, and let x star to be its limit. And what about En? Yeah, what can we say about En? On the other hand, we have already proved in the last theorem you see, you see, for every n we have already proved in the last theorem that mod En plus 1 is less than C delta delta mod En, right? And this was less than 1, right? So this will be mod En. But what was mod En? What is En? En is actually this is actually equal to En was, so En is negative, so these two imply that En is actually En plus less than equal to En plus 1, and we know that this is bounded above by 0, right? So hence En is a non-decreasing sequence bounded above by 0. So again, from monotone convergence theorem, it follows that this sequence also converges, and so we let E star to be the limit of En. Now passing to the limit, as n goes to infinity, in the equation, what do you get? You see, you have this equation, right? Xn plus 1 is xn minus f of xn by f prime xn, right? So if you do this, what will be r minus xn? It will be r minus xn plus f of xn by f prime xn, right? And this is precisely En plus 1 is En plus f of xn plus f prime xn, right? Now as n goes to infinity in this equation, so this is E star plus limit f of xn by limit f prime xn. See, because xn is a convergent sequence and f is a continuous function as well as f prime is a continuous function. What I want to say, we have already proved that xn is a convergent sequence, and we have assumed its limit to be x star, and since f and f prime are continuous, because f is assumed to be a C2R function, we must have that f of xn converges to f of x star and f prime xn converges to f prime x star as n goes to infinity. So this gives us that f x star is 0. Okay, but since the roots are unique, since f has a unique root, you must have that x star is actually equal to r. So hence what do we have proved finally? So finally we have that x star was this limit xn and this converges to r, and this finishes the proof of this convergence theorem for the convex function. Yeah. So the proof was derived from the previous convergence result from the Newton-Raphson method. Okay. Yeah. So maybe, okay, let us see. So in the Newton-Raphson method, you just see that this side, this side it should be noted that so from this equation, I'll write, because I just have to write a few lines. Now what does it mean? That xn plus 1 minus r by xn minus r mod square, it is actually mod of f dash xi n mod of this. Yes. So as n goes to infinity, why I'm using, just a minute. So from here, you see that this actually is a quadratic convergence in disguise. Okay, quadratic convergence. So Newton-Raphson method works better than the secant method because it has a quadratic convergence, whereas the secant method has convergence of order 1 plus root 5 by 2, which is the golden ratio. So we put one example forward to see that example. Okay, so our function is this. Now if we choose our initial guess to be, let's say x naught is minus 2.4, its root is minus 2. Okay, it is visible, right? Yes, so f of minus 2 is 0. So if we start sufficiently close to minus 2, let's say minus 2.4, then the iteration formula if you apply this iteration formula, xn plus 1 upon xn minus f of xn by f prime xn, so you will find that it is actually 2xn cube minus 1 by 3 times xn square minus 1. Okay, so it easily follows that you just verify that xn plus 1 r minus xn plus 1 by r minus xn square is approximately equal to 2 by 3, which shows the, see, because 2 is here, you just remember the definition, which shows the quadratic convergence of Newton-Raphson method. Of Newton-Raphson's method. Now so with this we finish the Newton-Raphson method. So So far, to solve the root of a linear equation, we have seen the bisection method, the secant method, and the Newton-Raphson methods. So in this spirit, we see the last method, and that is called the fixed point iteration method. So let us discuss it. It is called fixed point iteration method. So in fixed point iteration method, the problem of finding a root of a non-linear equation fx equal to 0 is equivalent to finding a fixed point of some other non-linear equation, okay, is equivalent to find a fixed point. What is a fixed point? A point is said to be a fixed point if fx is equal to x. Fixed point of a suitably defined function g. So this is how you convert this problem, and this is a very famous iteration method, fixed point. So let us first define what is a fixed point formally. So definition: let G be a continuous function on its domain, whatever the domain is. G be a continuous function. A point alpha in R is said to be a fixed point of G if alpha is same as G alpha, okay. So in practice, what happens, the idea is to rewrite the given equation fx equal to 0 rewrite the given equation fx equal to 0 in the form gx equal to x for some suitably chosen G. In general, there can be more than one choice of such G, as we will see in the following examples. So, if you consider fx to be this, x square minus x minus 2 is 0. You have to find root of this equation, okay? So, you see alpha is a root of f if and only if, if and only if alpha is a root of the functions defined as number 1, let's say g1x to be x square minus 2. Oh, sorry. If alpha is a fixed point, if alpha is a fixed point of each of the following functions defined below: g1x, second g2x is under root x plus 2, right? And third is g3x is 1 plus 2 by x. So each of this fixed point, if g1 has a fixed point, then f has a root and vice versa. It is easy to see. So the choice is not unique. Now let us start with the So the fixed point iteration method, for finding a root of gx equal to x consists of sequence of iterates xn starting from initial guess x naught defined by xn equal to g of xn minus 1. So we'll see that the function g is called the iteration function. So okay, so if let us see what do we mean by this. So we have this function, right? Fx equal to x square minus x minus 2, and let's say we choose our gx. So if we choose gx to be x square minus 2, then obviously we have discussed above, but okay, let us see. Then gx equal to x if and only if fx is 0, right? So if we choose our x naught to be, let's say, 0, then our x1 will be g of x naught, which will be minus 2. Then our x2 will be g of x1, which will be 2, right? Our x3 will be g of x2, which will be 2, and you keep on doing this. You see your xn from here onwards, it will be coming to be 2. So this iterative sequence, you see limit xn is actually 2, right? And here if you see f of 2 is actually 4 minus 2 minus 2, which is 0. So this xn actually converges to a root of the given function f. So yeah, but this was a very easy example. In totality, the picture is really different. So for this reason, we will now see the convergence theorem. Okay. Some technical glitch. Change layout. Okay. So theorem. Convergence result for fixed point iteration method. For fixed point iteration method. So let the hypothesis be the following. So let the iterative sequence, so the appropriately chosen iterative function g satisfies the following. be chosen so that number 1, G is a well-defined map from AB to AB, which means you have to fix in close interval such that BG is a self map. Second, G belongs to C1 of AB, which means continuously differentiable function. Third, G is a contraction. Now what does it mean? It means that supremum, or in this case maximum, because G is a continuous function, so supremum will be attained. So maximum of mod of G prime X in AB is less than equal to 1, and we assume it to be lambda. Then the conclusion is then number 1, x equal to gx has a unique root R, say R, has a unique root R in AB. Second, for any choice of x naught in AB, with xn plus 1 equal to g of xn, where obviously n belongs to n, we have that this limit xn actually converges to R. Third is that we further have that mod of xn minus R is less than lambda n mod x naught minus R, and which is further less than equal to lambda n by 1 minus lambda mod of x1 minus x naught. And thus you see that this will have a linear convergence, that is xn plus 1 R upon xn minus R is actually G prime R. Okay, so we have enough time, so let us prove it. The proof is simple. So why should one hold? Why should it has a unique root? Okay, so let us start. So from mean value theorem, you see R minus xn plus 1, which is g of R minus g of xn. Why? Because r is a fixed point of this. R is assumed to be a fixed point. Yeah. Why? The question is, okay, let us first prove. Okay, otherwise it will be 2. You see, if you consider the proof of 1, if you consider this function f of x as g of x minus b, okay, and x belongs to a comma b, so you have certain thing. This is a f is a continuous function on ab. F is a continuous function on AB, and what is f of a? F of a is g of a minus g of b, and because g is a self map from a to b, so the maximum it can go to b. So it is always smaller than and equal to, so this is 0, greater than equal to 0. Oh sorry, yeah. Oh god, what I'm doing. So this is actually negative, as g of x belongs to AB, which means g of x is less than equal to b. And what about f of b? It is, no, what I am trying to do is, g of b just a minute. Just a minute. Oh, G is assumed to be, okay, it is a self map, so G has to be, if like G of A, if you consider this function G of x minus x, then f of A, it will be like G of A minus A. Okay, sorry, so if you consider this function G of x minus x, so G of A minus A, it would be greater than equal to 0, right? And G of B, it will be less than equal to 0. Yeah, that was the problem. So basically it means that f is a continuous function, and because at one point it is greater than equal to 0, and at another point it is less than equal to 0. So by intermediate value theorem, which we call as IMVT, it follows that there is a root R between A to B such that f of R is R, f of R is 0, which means G of R is R. Okay, so it has a root, and we have used the continuity of the function G. Okay, now let us suppose that there is another root. Let R1 and R2 be two roots of f, then from again mean value theorem, what do we have? F of R1 minus f of R2 upon R1 minus R2, it will be equal to some f dash zeta, then zeta belonging to R1 comma R2. Okay, yes, and okay, let us first make sure that it has a root. Uniqueness we'll see later. Yeah, so from mean value theorem, it follows that modulus of R minus xn plus 1, which is nothing but G of R minus G of xn, the way we have defined the iterative sequence. Now it will be some G dash xi n, let's say, mod times R minus xn, but G is a contraction, so you will have lambda times R minus xn, right? And you keep on doing this, so you will get less than lambda n R minus x naught, and this happens for all n in natural number. Now So since as n goes to infinity, we know lambda n goes to 0. Why? Because lambda is strictly less than 1. Oh sorry, here we need strictly. Lambda n converges to 0. So this means we have xn converges to r as n goes to infinity. Okay, so you just verify this for a moment. So this gets settled down that the convergence is R. Further, okay, I think we have a very short period of time left. So let us see what we can do with this proof. No. So okay, let's try to finish. So yeah, so we moreover you see that mod of r minus x naught is actually equal to mod of r minus x1 plus x1. You know, by triangle inequality you can write this as this, right? And for r minus x1 we know it is lambda times r minus x naught, then plus x1 minus x naught. So this implies r minus x naught is actually less than 1 upon 1 minus lambda x1 minus x naught. Okay. Okay. Now if you again do this inductively you will get that r minus x1 is actually, we have already proved r minus x1 is lambda, oh sorry, r minus xn is lambda n minus 1. Oh, it should be n plus 1 here, yeah. So it will be lambda n, let's say this is 1, okay, let's say this is 1. So yeah, from 1 it follows that, so 1 implies this r minus xn is lambda n r minus x naught, and lambda r minus x naught we have just proved, you know, this part. So here we will have lambda n by 1 minus lambda times mod of x1 minus x naught. So this gives us this part of the proof. So we have proved one, uniqueness is still left, then we have proved this part. So the rest of the two part is left, which I think we don't have time for, maybe let us see how much we can prove. Okay, let us try to finish this theorem. So again, from mean value theorem, we get that r minus xn plus 1 is obviously, like r is gr and xn plus 1 the way I have defined this. Now from mean value theorem you will get some xi zeta n times r minus xn with xi n belonging to r to xn, or the other way. One conclusion that was coming from free, now we need here. So this already implies that limit xn converges to limit xn is r as lambda is less than 1 and is greater than 0. So this will imply limit r minus xn plus 1 by r minus xn, it is limit g prime zeta n. And you see, because as n goes to infinity, xn converges to r, which means zeta n will also converge to r, right? Because see, this lies between r and xi n, this lies between r and xn, let's say here, and xi n is here. Okay, so by sandwich theorem, xi n will also converge to r as n goes to infinity. Yeah, so this limit will actually be g prime r. Yeah, and I think this completes the proof. So uniqueness of r you should think about, okay, it's not difficult. So this completes the proof. So far what we have done in today's session is the following. First, we saw another in today's session we saw two methods for finding a root of non-linear equation. First is the Newton-Raphson method, and second is the fixed point iteration method. With these two methods, we saw the number one, the algorithm, the hypothesis, and the conclusion. Secondly, we saw their corresponding convergence results. For the Newton-Raphson method, it is quadratic. For secant method, we have seen it is 1 plus root 5 by 2. And for fixed point iteration, you should see why it should be linear. Okay, so with these root finding methods, in the last session, we might be discussing some interpolation methods which are also have been taught, and we'll try to do some exercises on that. So yeah, so this was it, and only one exercise is left, that why this gx has a unique root. Why this has a root, it has been cleared, okay, why this should happen. One rough idea is because this iterative sequence converges to r, and it will be true for any other root also, and since the limit is unique, so this r will be unique also. So one thing, if you can see why this way, or other way you don't need it, you just use the continuity. Okay. Yeah. So with this, so this was the convergence. Yeah, one thing we also have the convergence result for a special class of functions in the Newton-Raphson method, which avoids this paradoxical situation as to where to start the initial guess from. Okay, and that class is the class of strictly increasing convex function. Okay. Yeah. So okay, see you next time.